My name is Ramesh HG, working as Assistant Professor of Mathematics, Government First Aid College, Tiptur. Today I am going to explain a special type of algebraic structures, that is groups, in particular modular systems. In previous classes, you know what are groups, what are its properties and examples. So modular systems are also groups with a special binary operation applied on set of all integers. In this session, we shall introduce two types of binary operations on the set of integers. These binary operations are called addition modulo m and multiplication modulo m, where m is a fixed positive integer. These binary operations are denoted by plus m and into m. Let m be a fixed positive integer and a and b are two integers. The binary operation star is called as addition modulo m if a star b is equal to least non-negative remainder obtained by dividing the usual sum of a and b by m. Suppose if m is 5, if you add 4 and 3, we get 7. Then in place of 7, we have to put 2, because if you divide 7 by 5, the remainder is 2, like that. If m is 10, if you add 7 and 4, 7 and 4 is 11, then you put 7 plus 4 is equal to 1, because if you divide 11 by 10, we get remainder as 1. So that we call it as modulo m. So let m be a fixed positive integer and a and b are two integers. The binary composition star is called as addition modulo m if a star b is replaced by the least non-negative remainder obtained by dividing the usual sum of a and b by m. So a star b is replaced by least non-negative remainder obtained by dividing the sum a plus b by m. So if m is 5, if you add 4 plus 3 7, then you do not put 7. First you have to divide 7 by 5 and we get remainder as 2. Then you put 7 plus 4, 3 plus 4 is 7, that is equal to 2. That is called addition modulo m. Let m be a fixed positive integer and a and b are two integers. The binary composition star is called multiplication modulo m. Under multiplication, what happens? If a star b is replaced by least non-negative remainder obtained by dividing the usual multiplication of a and b by m. If m is equal to say 5, for example, if m is equal to say 5, and if you multiply 3 and 4 multiplication is 12, so we get 12. So 3 into 4 is 12. We do not keep it as 12. First of all, you divide 12 by 5, so remainder is 2, therefore 3 into 4 is equal to 2. That is, a star b is replaced by the least non-negative remainder obtained by dividing the usual multiplication of a and b by m. This is called modulo systems. This is called addition modulo m and multiplication modulo m. The addition and multiplication modulo m holds good commutative law and associative law. That you It is very simple. Addition modulo m and multiplication modulo m satisfies both commutative and associative properties. For example, in Z2 under addition, Z2 means it contains only 0 and 1. Z2 means it is a set, it is a subset of Z, it is a subset of Z. It contains only 0 and 1. And here binary operation is addition modulo 2. The binary operation is addition modulo 2 is a addition modular group. We call it as addition modular group. Here 0 acts as additive identity element and inverse of 1 is 1, because if you add 1 plus 1 we get 2. So you divide 2 by 2, we get remainder as 0. Therefore 1 plus 2 is equal to 2, that is equal to 0. And 1 plus 0 is 1. So only change is 1 plus 1 is 2. You divide 2 by 2, remainder is 0. Therefore you put 1 plus 1 as 2. So this is addition modulo 2 table. This is called multiplication addition table, addition modulo table. So you observe that 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, but you have to write it as 0 because 1 plus 1 is 2 and you divide 2 by m is equal to 2 here. So you divide 2 by 2, we get remainder as 0. So one can observe that all the elements of the group are 0, 1, 0, 1. It satisfies closure property. And it also satisfies associative property. It has 0 as acts as identity element. And the inverse of 0 is 0 and inverse of 1 is 1 itself. Because 1 plus 1 is 0. So 1 acts as inverse element of 1, that is self-inverse element. We call it as self-inverse element. So and hence it is an abelian group under addition modulo 2. It is an abelian group under addition modulo 2. Z3 under addition modulo 3. Z3 under addition modulo 3 is an abelian group under addition modulo 3. So addition modular group. Here it contains only 3 elements. We observe that Z2 contains 0, 1, Z3 contains 0, 1, 2, Z4 contains 0, 1, 2, 3, Z5 contains 0, 1, 2, 3, 4, etc. So Z3 contains 0, 1, 2. So here 0 acts as additive identity element. And inverse of 1 is 2. Because 1 plus 2 is 3, 3 divided by 3 we get 0 as remainder. So 1 plus 2 is equal to 0. And inverse of 1 is 2, inverse of 2 is 1. Here 1 plus 2 is equal to 0, 1 plus 1 is equal to 2. So you come to the table. So you observe that 0, 1, 2, 0, 1, 2 and add them. 0 plus 0, 0, this is 1, this is 2. Addition here, addition modulo 3. So this is 1, this is 1 plus 1 is 2, this 1 plus 2 is 3, that is equal to 0. So you divide 3 by 3, you get remainder as 0. 2 plus 1 is once again 0. 2 plus 2 is 4, you divide 4 by 3, remainder is 1, therefore you put 1. So you observe that all the elements of and these are the elements of the group Z3, that is 0, 1, 2. And 0 acts as identity element. 1 acts as inverse of 2, that is inverse of 2 is 1 and inverse of 1 is 2. So it satisfies all the properties: closure, associative, identity, inverse, and it also satisfies commutative property. So this is an abelian group under addition modulo 3. Addition modulo 3. Okay. Next, Z4. Z4 contains 0, 1, 2, 3 under addition modulo 4 is the addition modular group. Here 0 is the acts as identity element and inverse of 1 is 3 because 1 plus 3 is 4. So if you divide 4 by 4 we get 0 remainder. So 1 plus 3 is 0 and 2 plus 2 is 2 plus 2 is also 4, that is equal to 0, and inverse of 2 is 2, inverse of 3 is 1, inverse of 1 is 3, like that. So you come to the table, you observe that Z4 contains 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3. 0, 1, 2, 3. Add 0 plus 0. This is 1, this is 2, this is 3. 1 plus 0, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. We put 0. 2 plus 0, 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4, that is once again 0. 2 plus 3 is 5, that is once again 2. You divide 5 by 4, remainder is 1. 3 plus 0 is 3, 3 plus 1 is 0, 3 plus 2 is 5. It is once again remainder is 1 and 3 plus 3 is 6. Once again remainder is 2. So and hence these are the elements of the group G and hence it satisfies closure property and 0 acts as identity element and inverse of 1 is 3. Inverse of 1 is 3. Inverse of 2 is 2. Inverse of 2 is 2. Inverse of 3 is 1. So every element has its own inverse and hence it satisfies commutative property also. Therefore, it is an abelian group under addition modulo 4. Addition modulo 4. Algebraic structure, that is Z5 modulo system Z5. So it contains 0, 1, 2, 3, 4 is the addition modular group. So you come to this 0 acts as identity element and inverse of 1 is 4, inverse of 1 is 4 and inverse of 4 is 1 because 1 plus 4 is 0, this is 5. If you divide 5 by 5 it is 0 and 2 plus 3 is 5, that is equal to 0 and hence inverse of 2 is 3, inverse of 3 is 2, inverse of 1 is 4, inverse of 4 is 1 and hence it satisfies all the properties of the group. You come to the modular table. So 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4. Add 0 plus 0. This is 1. This is 2. This is 3. This is 4. 1 plus 0. 1. 1 plus 1. 1 plus 2. 1 plus 3. 1 plus 4 is 5. That is equal to 0. 2 plus 0. 2 plus 1. 2 plus 3. 2 plus 3 is 0. 2 plus 4 is 6, that is equal to 1. 3 plus 0, 3 plus 1, 3 plus 2, 5, that is equal to 0. 3 plus 6 is 1, 3 plus 7 is 2. So 4 plus 0, 4 plus 1 is 5, 0. 4 plus 2, 6. 4 plus 3, 7, it is 2. 4 plus 3, 8, that is 3. So all are the elements of the group Z5. And 0 acts as identity element and inverse of 0 is 0, inverse of 1 is 4, inverse of 2 is 3, inverse of 3 is 2, inverse of 4 is 1. Hence every element has its own inverse and it also satisfies commutative and associative properties and hence it is a group under addition modulo 5. If you take multiplication table here Z5 under multiplication, so it contains 1, 2, 3, 4 only. Non-zero elements, you have to take here non-zero elements. Z5, the non-zero elements 1, 2, 3, 4 is a group under multiplication modulo 5. Is a group under multiplication modulo 5. So Z5 under multiplication we have to take 1, 2, 3, 4 only, not 0. You do not take 0 non-zero elements. Non-zero elements 1, 2, 3, 4 forms an abelian group under multiplication modulo 5. Multiplication modulo 5. So you observe the table 1, 2, 3, 4, 1, 2, 3, 4. Multiplication here 1 into 1, 1 into 2, 1 into 3, 1 into 4, 2 into 1, 2, 2 into 2, 4, 2 into 3 is 6, remainder is 1. So you divide 6 by 5, remainder is 1. 2 into 4, 8, remainder is 3. 3 into 1, 3 into 2 is 6, remainder is 1. 3 into 3, 9, remainder is 4. 3 into 4, 12, remainder is 2. 4 into 1 is 4, 4 into 2 is 8, remainder is 3. 4 into 3, 12, remainder is 2. 4 into 4, 16, remainder is 1. So it satisfies closure property. And one acts as identity element. One acts as identity element. And inverse of 1 is 1, inverse of 2 is 3, inverse of 3 is 2, inverse of 4 is 4. Inverse of 4 is 4. So this acts as identity element. So 4 into 4 is 16, that is equal to 1. Therefore inverse of 4 is 4. So here 3 into 2 is 6. So we get identity element. Inverse of 3 is 2. Inverse of 2 is 3. And hence it satisfies all the properties of the group. Therefore it is an abelian group under multiplication modulo 5. You take Z8. Sorry, Z8. It is the integers 1, 3, 5, 7. 1, 3, 5, 7 forms an abelian group under multiplication modulo 8. Multiplication modulo 8. Okay, 1, 3, 5, 7. You take 4 elements 1, 3, 5, 7. Forms an abelian group under multiplication modulo 8. Multiplication modulo 8. You come to the table 1, 3, 5, 7. 1, 3, 5, 7. So 1 into 1, 1 into 3, 1 into 5, 1 into 7. 3 into 1, 3, 3 into 3, 9. You get remainder as 1. 3 into 3, 15, remainder is 7. This is remainder is 5. This is 5. This is 15, remainder is 7. This is 25, remainder is 1. So divide 25 by 8, we get remainder is 1. So similarly, all the elements of the groups are elements of G. Therefore, it satisfies closure property. 1 acts as identity element. Inverse of 1 is 1. Inverse of 3 is 3. Inverse of 5 is 5. Inverse of 7 is 7. So one thing you observe that all are self-inverse elements. So inverse of 1 is 1. Inverse of 3 is 3. Inverse of 5 is 5.